Hello, POE class. I just wanted to do a couple of calculations for you just to give you some help if you needed more guidance on the equations, the simple machine equations. So I'm going to start, if you wanted to follow along, I will do an example problem. I'll start on, let's see, number 4. So the wheel and axle. So it's important to know that whenever they're talking about actual mechanical advantage, they're talking about forces. So we're talking about force resistance over the force effort. Okay? So for example, when they ask you, well, first of all, this problem is a little tricky just because it says, hey, what is the linear distance traveled in one revolution of a 36-inch diameter wheel? It's kind of a trick question, but really what it's asking is, do you know how to do the circumference of the wheel, right? So one revolution of a 36-inch wheel would travel its circumference. What's the circumference? 2 pi r. Anybody? Anybody? So it is diameter times pi, because that's the same as 2 pi r, and I don't know, 113, maybe something around there. So that's just that one. Okay, we're going to sketch and annotate the wheel and axle. Oh gosh, this is going to be bad. All right, first we'll just go back. We'll sketch the wheel and axle. So I'll do a little, let's pretend this is the shutoff valve, and this is going to be the axle. So there's my circle for my handle. I need to turn that thing, and there's the axle. Okay. The second part of the equation is asking, okay, what's the actual mechanical advantage? Well, actual mechanical advantage, again, is going to deal with the forces. The ideal mechanical advantage is going to deal with distance. So the ideal mechanical advantage, which they're not asking for right now, is the distance effort over the distant resistance. So the distance of the effort arm over the distance of the resistant arm. But I don't think they even ask us that in this question. So let's take a look. Okay, there are 200 pounds of resistant force. Pretty simple, 200 pounds there. And there are 30 pounds of resistant force. Great. That right there is the actual mechanical advantage. Well, what's that? What's 200 divided by 30? You guys should be able to do this on the top of your head. That's why I'm going to quickly do it on the top of my head. Let me click here for the top of my head. And we have, that's right, 6.67. We'll say that. So 6.67. And that is our actual mechanical advantage. Because we're just assuming that a 30 pounds of force is able to just turn the wheel. Now, then it asks, okay, what is the wheel, what is the required wheel diameter to overcome the resistant force? So this kind of has to do with our static equilibrium problems. So static equilibrium problems are dealing with both the force and the diameter because we're talking about the moment. So let's pretend like we're looking at this wheel straight on. Okay, we have a wheel right here, straight on, and we have that middle part there. And let's change that to be like a lever example. Oops. So here we go. Instead of doing it like that, let's look at the very center as the fulcrum, okay? And then off of that fulcrum, we have our second class lever. Oh, this is kind of interesting. So this would be the radius of the wheel, okay? The radius of the outside wheel. And we'll pretend like this is the radius. That there to there is the radius of the inside wheel. So picture this is a big wheel, okay? So this is my resistant effort. That's the distance to my resistant effort right there, which we know is 200 pounds. Okay, and we also know that this right here is the radius of that diameter, which is going, the radius is going to be 0.75, because in our equation it says the valve will encounter 200 pounds of resistant force applied to a 1.5-inch diameter axle. So we know that the radius of that axle is 0.75. So the distance from the fulcrum to the resistance is 0.75. We've just turned this into a lever problem. And then it's going to, we know that our the edge of the wheel where our hands are, we have applied 30 pounds of force right here, 30 pounds of force. So again, we're going to look at this like a algebra equation. So on one side of the equation, we have a resistance of 200 times 0.75, which we know, gosh, from just basic math, we know that on one side of the equation we have 150 pounds of resistant force, 200 times 0.75. And then we know that on the other side of the equation, what we have to, our effort arm distance is 30 times, our effort arm is 30 times what? This is what we're looking for. So we're doing a basic algebra problem where we say, hey, get, x by itself, or the question mark in this case, because I'm not a math teacher. So we're going to take 30 So 150 divided by 30, what does that equal? We already know. It's 5. 5 inches. So the radius, the distance from the center of the fulcrum, or the center of the wheel on the fulcrum, to the edge where my force is applied is 5 inches. It has to be that distance for us 30 pounds of force to start to move it. That's the very minimum, I guess. So, but that's the radius. So the question at the very end is asking, what is the required wheel diameter to overcome the resistant force? 10 inches, just over 10 inches, I guess, would be the real answer, because this is the radius. The diameter is 10 inches. This is also the same kind of scenario as static equilibrium problems, okay? So it's really the static equilibrium problem asked in a different way. I hope this makes sense, and yeah, email me if you have any questions. We'll go over this on Tuesday.